last time, we tried to calculate physical observables within the Hartree-Fock theory to compare with the experimental observations. And in particular, at the end of the lecture last time, we calculated quasi-particle excitation energy within the Hartree-Fock. And in addition to the free electron kinetic energy term, we also have this Hartree-Fock exchange energy, which will contribute to the quasi-particle excitation for a single electron. And that exchange energy will lead to a jump of this excitation energy right at Fermi momentum. And that jump will lead to the divergence of the denominator of the density of states, which leads to the vanishing of this density of states, and which is certainly wrong, because we know that this weakly interacting, Coulomb interacting electron gas in metals shows constant density of states at Fermi surface. So the Hartree-Fock prediction is completely wrong. And let's just look at the other wrong predictions within the Hartree-Fock. And another quantity that is related to quasi-particle excitation is the bandwidth, where if you plot this density of states as function of temperature within Hartree-Fock or any other framework, you will find that there's finite range in energies that you have finite density of states distributions. So the distribution of the density of states defined, the width of that distribution defines this bandwidth. We know that for free electron gas, the bandwidth is just a constant, which is defined as, roughly speaking, this quantity. So if you just have this kinetic energy term, but within the Hartree-Fock, this is given by so-called the Hartree term, which is only the kinetic energy term that leads to the bandwidth. So there's additional contributions from this exchange energy. So if you compare this bandwidth of several metals between the experimental results and the Hartree-Fock, you will see that this agreement is really bad. So you'll see very clearly that if you have just the first term, which we call this Hartree term, which is simply just a free electron kinetic energy term, and that will lead to a bandwidth which is much closer to the observed values for lithium, sodium, and barium. And if you add this exchange term or the Hartree-Fock term in that bandwidth calculation, you'll get even worse values compared to the observed value for the bandwidth. So the reason is precisely because of this stuff here. Okay, so the exchange term from this Hartree-Fock theory will lead to the much more worse results for the bandwidth. Okay, so more seriously, if we calculate the specific heat, which we call CV, divided by the energy, the derivative of the energy of the system with respect to temperature, and this quantity within the Hartree-Fock theory is proportional to a divergent quantity, temperature divided by log of temperature. So you will see immediately that this quantity gives you what? When t equals 0, this is t over log t. So log 0, 0. Okay. Anyway, so this quantity t over log t is very different from the normal Fermi liquid, which is proportional to linear in temperature. So I don't have time to calculate this specific heat within this Hartree-Fock, but You can find this in the literature or reference books, that there is a logarithmic temperature dependence in the denominator of the specific heat within the Hartree-Fock, and which is very different from very simple of normal metal in specific heat, namely the linear in temperature. Okay, so a very important properties of normal metal in specific heat is that if you divide the CV by temperature, it is a constant proportional to density of states at the Fermi level for ordinary metals, which we call this Fermi liquid properties, that the CV over T, which we call the specific heat coefficient or gamma coefficient, is a constant proportional to density of states. But here, the specific heat coefficient actually behaves very singularly because of the logarithmic temperature dependence in the denominator. Okay, well, that's the dead end because of this wrong starting point that Hartree-Fock takes, and that leads to a totally incorrect predictions when we compare to the experiments. So the last thing that we like to emphasize is the favors of ferromagnetic ordering within the Hartree-Fock. As I mentioned previously, that we have only two possible spin orientations when we talk about this Hartree-Fock scattering by Coulomb, namely either all the spins for the four electron states are pointing up or all pointing down, because the spins should be conserved at each of this interaction vortex, so we cannot create or destroy the spin in this scattering process because the Coulomb interactions are spin independent, okay, within the Hartree-Fock. So the Hartree-Fock theory actually ignore the correlation or interaction between spin up and spin down, and therefore it favors ferromagnetic ordering. Okay, so let's see how this results comes about. So we can compare energy of a ferromagnetic ordered states, within the Hartree-Fock, and the non-magnetic state. So we know very well that if we have a ferromagnetic order, as I mentioned last time, all the spins are in parallel to each other, but we are talking about metals, right? So if all the spins are pointing to the same directions for this electrons in the metal, ferromagnetic metal, so you have only one electron populated per level, right? So you cannot have doubly occupied states, because if this is the case, then spin up and spin down will get cancelled. So you won't get a fully polarized ferromagnetic ordered state, and therefore all the spins should be pointing either up or down. And compared to a non-magnetic metal, you have only, say, partially filled orbitals, right? So at each orbital, you could populate two electrons with opposite spins, right? So then you could have either all paired electron states, or you have some unpaired, just one level that there is a single electron populated there. Okay, so suppose we consider just a non-magnetic metal where all the number of electrons are even, so then all the spins are pair up, okay, like this. So you immediately see that the total energy levels here is actually, for ferromagnetic metals, the total number of orbitals or levels are twice as large as the total number of non-magnetic metals, because suppose we have even number of electrons, okay, and occupy total n levels. But if you simply just want to fully polarize this even number of electrons in that orbitals, then total number of orbitals should be 2 times n, right? Okay, so which means that your Fermi volume is actually twice as large as in the ferromagnetic case compared to the non-magnetic. Okay, suppose this is, say, this volume for non-magnetic, and for ferromagnetic metals, it is 2 times the non-magnetic, right? As a result, the Fermi momentum, Kf, is actually bigger in the ferromagnetic case compared to non-magnetic case, and bigger by 2 to the power 1/3, because this is the 3-dimensional Fermi spheres. So the total volume in the ferromagnetic case is actually twice as large as the non-magnetic case, and therefore this Fermi momentum, or the radius of the Fermi sphere, is larger in the ferromagnetic case by a factor of 2 to the power 1/3. Okay, so you can compare the energies of these two different states and which one gives you a lower energies. And so the total energy consists of the Hartree term, which is the kinetic energy term, plus the exchange term, or the Fock term. Right, so you can calculate this quantity, the total energy of this ferromagnetic states and non-magnetic states for metal, and you could just see which one wins. You know, when I say wins, it means that the total energy is lowered. Okay, so the ground state belongs to the state that has the lower energy. Okay, so you will see later that within the Hartree-Fock, this ferromagnetic metallic ground state is always the ground state for certain conditions, and that conditions can be satisfied very easily. So, which means that it predicts many ferromagnetic metals in the realistic materials, but unfortunately not that many metals are ferromagnetic. Okay, so let's take a short break. When we come back, we will outline how we could distinguish the ground state within the Hartree-Fock between this ferro or non-magnetic. Okay, so let's finish this comparison. So suppose we calculate the energy difference between the ferromagnetic metal and non-magnetic metal by subtraction their total energies, and we can compute this delta E. If this delta E is negative, which means that the ferromagnetic ground state is actually the true ground state, because this energy is lower than the non-magnetic state, and vice versa. So if this quantity is positive, then it is the non-magnetic state which has the lower energy. Okay, so if this quantity is plus and the ground state is non-magnetic, and negative is a ferro. Right? So let's do the algebra very easily down. So this energy consists of two terms, the kinetic energy and the exchange energy, or the Fock term, right? And you simply just separate these two contributions and subtract these two different states. And remember that for ferro, the Fermi momentum becomes larger by a factor of 2 times 2 to the power 1/3, and also for the exchange term. So plug in this kinetic energy and exchange energy, and you'll find that this is their difference, which has two terms. One is the term that comes from the kinetic energy, another is from the exchange energy, and you'll find that this difference is given by this quantity. The first term is some number over 1 divided by Rn squared, and the second term is 0.2 divided by Rs in units of Rydberg constant. So this quantity could be either positive or negative depending on how large is Rs. Okay, so if the Rs is actually smaller than the critical value, which means that the critical value is when this is 0. So if the Rs, remember what is Rs? Rs is average radius of this electron, right, relative to the nuclear core. Okay, so if the average electron distance to the nuclear core is actually less than some critical radius, then the non-magnetic state wins. But if this is larger than the critical value, then this ferromagnetic ground state wins. But to satisfy this condition, you find that there are many metals that satisfy this condition. So if the Hartree-Fock theory is correct, then those many metals will have ferromagnetic order at ground state. Okay? But the fact is not so many metals show ferromagnetic order. And in fact, there are only very few examples in metals that shows ferromagnetic order, and therefore the remaining metals actually are non-magnetic. So the Hartree-Fock theory incorrectly predicts that there are more metals than there actually are that show the ferromagnetic order. Okay? So in other words, the Hartree-Fock theory overestimates the ferromagnetic order in Coulomb interacting electron system, especially in normal metals. And the reason why this Hartree-Fock theory overestimates the ferromagnetic order is precisely because of the way that they treat this Coulomb interaction as a weak perturbation and relative to the unperturbed eigenstates of the kinetic energy operator. So we need to totally give up the Hartree-Fock completely, because it doesn't describe correctly this Coulomb potential. Okay, so the Coulomb potential is treated incorrectly within the Hartree-Fock. And so what is the correct treatment? As I mentioned many times, that we need to really consider the small density variations or fluctuations in metals, and which will lead to the screening of a Coulomb potential. So we need to take care of the screening effect. Okay, so the correct approach to address the Coulomb interactions should take care of the screening. Okay, so let me just illustrate the physics of this Coulomb screening. As I have mentioned probably previously, that we are talking about the many-body system in solid state, where we have a bunch of ions sitting in a periodic array in three-dimensional space and surrounded by many electrons, right? So we have many negative charge electrons, but also have many positive charged ions, right? So when we study the Coulomb interaction between any two electrons, we cannot ignore the presence of other types of electrons or charges. For example, if you consider the electron over here and electron over there, which I call this electron number 1 and electron number 2. Okay, so if we have just these two electrons, then it's very naive. We know their potentials, 1 over r. Okay. However, things that are not that simple, because we know very well that in between these two electrons, there are so many other charged particles in between, right? for example, you have many, many electrons in between these two electrons here and there, and you have many, many positive charge ions, right? So these negative charge electrons and positive charge ions will interact with either both electron 1 and also electron 2. Okay? So therefore, the Coulomb potential that's filled by electron 1 or electron 2 is not that just the single Coulomb potential between these two electrons anymore. It's a sum of all possible Coulomb potentials in between. So then for electron number 1, the net Coulomb potential is the bare one plus all the other Coulomb potentials in between. Likewise, for electron number 2, is this term, the bare term, plus something else, and that something else is going to modify the original bare Coulomb potential in a way that they don't feel that much Coulomb energy anymore. Okay, so the magnitude of the net Coulomb potential between electron number 1 and number 2 is actually much less than the bare Coulomb energy. When I say bare, I mean you simply just consider these two electrons and nothing else, and they interact by Coulomb like this. This is called the bare Coulomb potential. So the other Coulomb potentials, other than the bare potentials, is going to cancel much of the bare Coulomb potentials, so that at the end of the day, the magnitude of this net Coulomb potential between 1 and 2 will be much smaller than the bare value itself. So in a way, there are cancellations of many Coulomb potentials in the realistic solid state systems. And these cancellations, we can estimate this later by semi-classical approach and also by the pure quantum mechanical approach, will lead to the screening of Coulomb. And this screening, in fact, is the key that leads to the failure of the Hartree-Fock, and also leads to all these incorrect predictions within the Hartree-Fock. Okay, so we need to take care of this screening effect seriously and estimate the net Coulomb potential between any pair of charged particles in solids, and we find that this many-body effect is going to modify or renormalize the bare Coulomb potentials significantly, so that this Coulomb potential becomes short-ranged. Okay, so in other words, the Coulomb potential does not work as just 1 over r for arbitrary large r anymore. So it will be cut off when the distance between any two charged particles exceeds a critical, say, distance. So for this very long-range charged particles, they don't feel much the Coulomb energy anymore because of the screening effect. So let's take a short break. When we come back, we study this screening of Coulomb potentials by a semi-classical so-called Thomas-Fermi approximation. And then we will treat this purely quantum mechanically, and then we can find out the correct language to rewrite the Hamiltonian of a Coulomb interacting electron gas. So I think you are not so unfamiliar with screening of charges in your electrodynamics. You know very well that many materials have different dielectric constants, right? And if you place the test charge close to some material, then there will be induced charge distributed at the surface of that object, which tend to cancel that test charge. Okay, so that cancellation of the test charge is precisely called the induced screening effect, so that the net charge near the surface is actually less than the test charge. Okay, so this is the classic example of this screening of a charged object. So let's talk about the screening. So first we should take this semi-classical approach to illustrate this physics of the screening like this. And this semi-classical treatment is called the Thomas-Fermi approximation. So which means that we combined classical electromagnetism and some quantum mechanics. So it's a mixture of classical and quantum mechanics. So we consider, again, some charge distributions in real space, and we could put some test charge, and we study the induced charge due to the presence of the test charge, and then we solve the Poisson equations in classical electrodynamics, results from the Schrödinger equations. So it's a mixture of the two. Of course, this is not an exact treatment of the problem, but it gives us some intuitions because we are familiar with the classical electrodynamics. So suppose I study electron response to a static charge Q in a plasma. By plasma, I mean there are many, many charged particles distributed in real space, and we assume that the spatially inhomogeneous charge disturbance varies only little over an atomic spacing. We also assume that the Fermi energy is also slowly varying in space. We could plot this kind of starting point in this figure here that we consider a very smooth charge fluctuations in solids, and this variations of this charge disturbance, like this wave-like disturbance, is actually very smooth within the lattice constant A. Okay, so it's very slowly varied charge disturbance in space. And in that system, we put the test charge. Suppose there's a test charge. And we get some external charge, which is very close to this spatially variant charge distributions. And we know very well that this test charge is going to induce charge variations, delta rho, on the original charge distributions. So in other words, the test charge will induce charge perturbations, which I call this delta rho, in the original charge distributions. And under such assumptions, okay, so the Fermi energy is also slowly varying in space, which means that this momentum Q is actually much less than the Fermi momentum, which means that this small variations of charge in real space, if you Fourier transform this, this charge disturbance, and it gives you some wave number Q, and this wave number Q is actually very, very small, which means that this is a long wavelength limit. This charge disturbance in real space is actually very, very, very slowly, and if you transform this to the momentum space or K space, it corresponds to very long wavelength limits of momentum transfer, and this momentum of this charge disturbance is much less than the Fermi momentum. So that's for the sake of the later calculations. If this is the case, then we could simply just write down the equations based on the Schrödinger equations for such a system, for say a single electron in such charge distributions. And we know that this Fermi momentum is also a function of real space variables because imagine we have locally varying functions in space for these charge distributions. So remember this from the Schrödinger equation, we got total energy, which is kinetic energy plus the potential energy, right? So then if this epsilon f is the, say, the total energy, and this term, h bar squared kf squared divided by 2m is the kinetic energy, and it's minus E times the psi of r, the potential, is the potential energy. So from Schrödinger equation, we have such a relation, right, among the Fermi energy and the potential energy and the kinetic energy, right? So let me just write down this Poisson equation. So the first condition is from the quantum mechanics, from Schrödinger equation for single charge particles, but we could combine this with the classical electrodynamics, which is the Poisson equation. Then in the Poisson equations, tells you the relation between the charge distributions and the Coulomb potential, right? So the Poisson equation has this form saying that this Laplacian, or the gradient square of the net potential, is given by this charge, the point charge, test charge Q, at this position r equals 0, where there's a delta function here. And of course, there's another contributions from the charge, fluctuations. So remember, the total charge of the system is given by the sum of these two terms, right? So remember, delta rho is actually opposite to the test charge. Okay, so if you place a positive charge, in the vicinity of some object, and the edge of this object will induce a negative charge to cancel the external positive charge that you impose to the system. So the induced charge takes a minus sign relative to the test charge, and that's why you get this, opposite sign here. This is a minus sign for the test charge Q, but this is a plus sign for the induced charge. So let's take a short break. When we come back, we will combine these two equations based on quantum mechanics and so classical electrodynamics, and also taking advantage of such approximations, like assumptions here, and then we could calculate this consequence of these two equations, and we can solve the net potentials psi of r, and then we know that this psi of r is no longer simply just 1 over r potential anymore. Okay? So let's take a short break. Okay, so let's continue. As I mentioned, we combine classical electrodynamics and quantum mechanics by solving these two equations simultaneously to get solutions for the net potential in this charged plasma, and this delta rho represents the change in electron density near the test charge Q because of this test charge Q. And this electron charge density as function of r could be considered as just a uniform charge or average charge distributions, which is a constant independent of r, and plus the small variation delta rho, which is precisely this delta rho. And this charge density in quantum mechanics could be evaluated by this volume of the Coulomb spheres, right? So the total number of electrons is proportional to the Fermi volume, and the Fermi volume for just a spherical shape of the Fermi surface is given by the volume of the sphere, right? Okay, and the radius of the Fermi spheres is given by this Fermi momentum kf. And so the density of the charged particle is given by the physical volume in the denominator, and in the numerator is the number of electrons. So rho is given by number of electrons divided by the real space volume, but this number of electrons could be estimated by the volume of the Fermi sphere. And therefore, you could derive such a relation from this sort of a quantum mechanics, the Schrödinger picture of a free electron gas, given by this kf's cubic term divided by 3 pi squared, which comes from these two relations here. Okay, but what is kf? Well, kf could be replaced by this equation number 1, which is square root of this kf plus E5 and multiplied by some factors. But this is a cubic term. Therefore, the overall exponent here is actually 3/2. Okay, 1/2 cubic term, which is 3/2 exponent. But this rho of r is given by a uniform charge distributions plus some small variations, delta rho, and therefore you could get the relation between delta rho and this Fermi energy and also the net Coulomb potential. So we assume that this potential energy is much less than this Fermi energy. In such a case, we could Taylor expand this power of epsilon f plus E phi to the 3/2, and we Taylor expand this. Namely, we linearize this equation. We get this relation here. We only keep the expansion to the linear term in n and E phi. So now let's just plug in this delta rho back to the Poisson equation. Let's just plug in delta rho here back to the Poisson equation and Fourier transform this. So then this Poisson equations becomes this equation. So you simply just plug in this delta rho back to the Poisson equation and rearrange these terms, and you get this modified Poisson equation. And this equation can be easily solved because we can Fourier transform this psi of r and delta of r in k-space. We Fourier transform this equation in k-space. So when we do that, we simply just Fourier transform this. We could Fourier decompose this net potential in Fourier component like this. And then we could very easily verify that this is given by e to the I k r 6 pi n e squared divided by epsilon f. And you simply just take the Fourier transform of this quantity summing over k, and you get your new Coulomb potential in terms of the real space. Variables are, so here KTF is so-called Thomas-Fermi screening wave vector, which is given by this quantity. So this is just a simple exercise to all of you. If you learn a little bit of this electrodynamics, you could solve this so-called Poisson equation, the Laplace equations, by Fourier transforming this equation on both sides from real space to the momentum space. So this gradient square in k space becomes k square. So you could very easily solve this real space and momentum space of the potential, and this the solution based on the Thomas-Fermi approximation is given by this expression, which is e to the minus r divided by lambda Thomas-Fermi. Well, lambda Thomas-Fermi is actually inverse of k Thomas-Fermi. So it is the characteristic distance between two charged particles. And this distance is actually a critical distance over which the Coulomb potential decays exponentially. In k space, psi of k is given by 4 pi q divided by k squared plus k Thomas-Fermi squared. Okay, so this is an important relation in Coulomb interacting electron plasma in the semi-classical treatment, that you find this Coulomb potential between any two charged particles behaves like the so-called Yukawa potential. And in momentum space, this remember the unscreened paired Coulomb potential in k space is proportional to q squared, but there's nothing here in the denominator to add to this q squared. So in other words, when q goes 0, you get infinity and you get a long-range Coulomb force because of this 1 over q squared. However, if we take into account the other charged particles that also contribute to the Coulomb potential between any two charged particles, and that contributions are going to give you a cutoff in the denominator of psi of k, in the sense that when k goes to 0, there's still something finite remains in the denominator, which will not lead to the divergence of this psi of k. Okay, and this K Thomas-Fermi is given by this combination of this electron average density, electron charge, and Fermi energy. So for different metals, you could estimate this value of K Thomas-Fermi. So if you make a plot of this screened Coulomb potential compared to the unscreened version, and you'll see that this function actually decays very fast when this distance is over this lambda Thomas-Fermi. So when the distance between any two charged particles exceeds that critical value, these two charged particles will feel almost nothing, only just exponentially decayed Coulomb potential between them. So this is V Thomas-Fermi, and this is V bare. Okay, so unlike this screened Coulomb potential for the unscreened Coulomb potential, so no matter how long, how far away these two charged particles are, they always feel the 1/r potential without any screening effect, which is certainly wrong, because the presence of the other charged particles certainly influence any Coulomb potential between any two charged particles. And that influence is actually captured by this Thomas-Fermi approach, semi-classically, in a way that if these two charged particles are too far away, they don't feel each other. They don't feel the Coulomb potential between them because of the screening effect. And this characteristic length scale over which this Coulomb potential decays is called lambda Thomas-Fermi. And this behavior should be respected, because that's what happens for the realistic solid-state material, that the Coulomb potential is screened, not unscreened. And this is precisely the reason why the Hartree-Fock theory fails, because there's no way that within the Hartree-Fock that you could get such physics. However, there are some remarks to be said, because this Thomas-Fermi approximations is just a combination of a classical and quantum mechanics, so it's not purely quantum mechanical results. Okay, we know that if we really want to capture the physics of solid state, we need to really address these quantum mechanical aspects. Okay, so in a way that the semi-classical treatment only capture in spirit the quality features of the decay of a Coulomb potential, but there are still some phenomena that cannot be captured by the Thomas-Fermi. Okay, so we will see these shortcomings of this semi-classical treatment in just a moment. So you could check these corresponding chapters in Kittel's second book and David Pine's lecture notes. Perhaps in Flansburgh also have that chapter. Okay, so let's take a short break. When we come back, we will mention some remarks which states the limitations of this Thomas-Fermi approximation. Is everything clear? I mean, the physics is really clear that we cannot naively consider an unscreened Coulomb potential in a more realistic description of metals. We need to take care of this, take into account this physics. So later we will treat this screening purely quantum mechanically, so that you know how powerful this second quantization approach is. Okay, so without the second quantization, it's certainly not easy to capture this physics quantum mechanically. So I hope that you will get a complete picture of what I'm going to tell you and get the correct physical pictures of this phenomena. Please remember that physics is actually experimental science. Okay, so we always need to think about the physical phenomena. Okay, in the first place. Okay, so the purpose of the theory is to help us to understand this phenomena, and almost all this very complicated physics phenomena could be understood in terms of the plots, the figures and graphs, and therefore it is very important that we get a good physics intuitions, and this intuition comes from the fact that you could visualize everything, and not by the equations, but by the pictures and graphs and plots and so on. And as I mentioned many times, that when you think about this Coulomb scattering, what in your mind should be this diagram here. Okay, so when you talk about the screening of a Coulomb potential, the first image that comes to your mind should be this cartoon picture that I show over there. So in all cases, it is very important to think about the physical phenomena in terms of figures, plots, pictures, graphs, and so on. A very important criterion to ask yourself whether you understand this physics or not is very simple. The question is, can you plot this phenomena? Can you use figures? Can you use the graphs to understand this physics? If you cannot use any plots or figures or diagrams, that means that you do not understand completely at that point. Okay, so almost all physical phenomena could be visualized, could be studied, or could be understood in terms of pictures, graphs. So you should always get the physical pictures. So the first question in your mind is, what is the physical picture of something? Okay, so unless you can have very clear physical pictures, you don't understand this subject. So it's not that you understand the equation, no. You should visualize this phenomena in your mind. It's not the equations that come to your mind first, but the pictures, always pictures and graphs and diagrams. So let's just make some remarks of Thomas-Fermi. So the first requirement is that Thomas-Fermi approximation requires the slowly moving electrons, so that electrons actually give rise to only static disturbance, which means that all these electron distributions in solids within this Thomas-Fermi assume that these electrons move very, very slowly, so that the electrons only give rise to a static charge disturbance rather than dynamic, meaning there's no charge fluctuations in time, but only charge fluctuation in space. So that's the assumption behind Thomas-Fermi. But that assumption is not correct. So we will make that point later. So the second requirement is that the Thomas-Fermi approximation requires the linearized procedure to be valid, meaning the potential energy is much less than the Fermi energy. So remember, the Rs is actually the distance of electron relative to the nuclear core, and that units of Rs, and R0 is the electron radius. Okay, so which means that this is the assumption that allows us to linearize this Poisson equation. Remember that. Okay, but this assumption leads to the following consequence. Okay, so if you plug in all this, numbers in, say, Fermi energy in terms of the electron radius and Bohr radius and so on, so you'll see that this condition implies that this inequality should be valid. And now you could rearrange this inequality, which tells you that this Rs should be much less than 1. Remember, in ordinary metals, Rs is somewhere between 5 and 2. But this, this Thomas-Fermi approximation requires that the Rs electron radius is actually much smaller than the radius for ordinary metals, which is also not realistic enough, but just the assumption. Okay, it's a mathematical assumption which is not true in many cases, but it's just an assumption that allows us to do some approximation. So you should always be careful that this assumption is not always correct or accurate. And so the Thomas-Fermi requires very high density. Very high density. It's much higher than the density of electrons in normal metal, and therefore, for that reason, this Thomas-Fermi is not that accurate description, but it captures some qualitative behavior of the Coulomb screening, but quantitatively is not correct, is not accurate, because precisely those assumptions not true. So number 3, so this Thomas-Fermi looks only at the long wavelength behavior, meaning this momentum Q is much less than this Kf. So the fluctuations in electron density vary very slowly in space, which means that in Fourier component, this momentum q associated with this delta rho is really small, which means that we only care about the long wavelengths because this momentum q is actually inverse proportional to the length, the wavelength, right? Okay, so the longer wavelength, the smaller the q. So we only look at the smaller q limits of this charge distributions, and for which the assumption of slowly varying potential is valid. So in the long wavelength limit, this assumption of slowly varying potential can be valid. But we have different fluctuations with different wavelengths. We have long wavelengths, we may have intermediate wavelengths or short wavelengths limit fluctuations, but these shorter wavelengths behaviors are totally neglected. So in reality, the electrons in real solids are not moving slowly. So they are moving very fast. Therefore, the charge fluctuations in realistic metals shows both spatial fluctuations and time fluctuations in temporal degrees of freedom. So we need to address the response of electrons to a time varying disturbance. And later we will study this time varying fluctuations of charge, and we call this plasma oscillation phenomenon. So let me just illustrate these ideas in a cartoon picture, what I mean by the time varying charge fluctuations. So we know very well that this all charged particles, electrons and ions satisfy in general this quantum mechanical principle, meaning the Schrödinger equations, even though we don't have solutions for them individually, but we know that those electrons can actually move very quickly, and so this charge disturbance distributed not only in space but only in time. So which means that delta rho is a function of both spatial coordinate r and time coordinate t. And in Thomas-Fermi approximation, we can only address the spatial variations of the charged particles by combining the classical and quantum mechanics, and we cannot address this delta rho as a function of time, and we should do it purely quantum mechanically. That can describe this delta rho as a function of time. So the charge distributions in the fixed location is also a function of time, and it is a periodic function of time, and the oscillations of charge distributions at the fixed locations periodically as a function of time, and that phenomena is called plasma oscillations. And the physics of the plasma oscillations could be understood very easily from this cartoon picture. Remember, as I mentioned, there are many ions, positive charge ions, sitting orderly periodically on the lattice, and there are many electrons surround such an ion core, and those charged particles, say electrons, clouds that surround the ion core may fluctuate in space and also in time. So let's talk about the time fluctuations. Okay, so we know the spatial fluctuations could be quantitatively described by the Thomas-Fermi, but what about this temporal fluctuations? So the electrons satisfy this Heisenberg-Stirling principle and also Pauli principle and Schrödinger equations and so on. So these electrons are quantum particles. So they should satisfy this quantum mechanics, and then one of the quantum mechanics principle is Heisenberg uncertainty principle, which means that you cannot determine the location and momentum simultaneously 100% accuracy for any quantum particle. Okay, and that leads to the fluctuations of charge densities or particle densities in time. So we could solve this so-called the Heisenberg equation of motion, which we will do that later. Okay, so we know this evolution, time evolution of electron density in time. And this is the way that we will take to solve this density fluctuations in time quantum mechanically. But the physics could be very easily understood in terms of such plasma oscillations. And suppose I have an ion carrying positive charge in the middle, and this positive charge will certainly attract negative charge electrons because they are attractive to each other, right? Okay, so when they are attractive, these ions are very heavy, so they cannot move. Just very slowly, very little they move, but electrons can move, okay, because they are lighter. Okay, so the less heavier particle electrons can actually move closer to the ion core because they are attractive to each other. So as a result, you will see that the electrons are moving closer to the ion core in response to such attraction between these two. Okay, but somehow the electrons overshoot. They come too close to the ion core. And we will study this overshoot phenomena from the quantum mechanics treatment. So those electron clouds move very quickly and get much closer to they should do relative to the ion core, so that you get overcompensate negative charge. So the net charge is negative again because the electrons, the more than enough electrons come to the ion core to cancel this positive charge, but this number of electrons are much more than necessary. Okay, so they overcompensate this positive charge, and as a result, if you look at this net charge of everything inside this red circle, you find that this net charge is actually negative. Okay, and this is unstable, and as a result, this negative charge clouds will attract positive charge again. Okay, so this will lead to another overshooting charge moving from the surrounding ion. Okay, so and therefore you get again overcompensated positive charge because of the ions can actually move closer to the this negative charge cloud if the electrons overcompensate this ion in the first place. Okay, and that's becomes a circle. Okay, because now you can see that you have more positive charge again, right? So the electrons will actually move back and forth between this overshooting negative charge and overshooting positive charge. Okay, so therefore electron density actually fluctuates in time. If you take a snapshot, the picture of this electron distributions in solids, you'll find that sometimes you get this picture and sometimes you get that picture, but the change between these two cases is actually periodically modulated in time. And this is the origin of the density fluctuation or the plasma oscillations. And of course, you could have electron hole pair excitations, right? So you may have some electron hole pair excitations, right? And this hole comes from the electron state right below the Fermi surface, and sometimes this electron hole pair got merged into the occupied electron states, and so that your excited electrons are gone. So you can consider this also some kind of a oscillation in time that over time you could create electron hole pair excitations, but these excitations are not stable, so they may decay. When they decay, you get less electron numbers, okay, than before, and therefore you get less electron charge to compensate this, say, the ions, and therefore the ion may behave like positive charge again. And so we will address this issue when we use this proper language, which is the density of the electron, right? So this implies that the proper language to address this, both the, say, the screening of electron potential and also the plasma oscillation is this quantity here rather than the Coulomb potential itself. So it is the density of electron that's fluctuating, and these fluctuations are considered as small perturbations. Okay, so these fluctuations are really not that big compared to the uniform charge distributions in time and space. So you see that this amplitude of this charge fluctuations you'll see next time is not that large. It's really small. In other words, the density operator itself and the change in electron density in the second quantized language is the key. Okay, so we need to re-express everything in terms of electron density operator. Okay, so electron density operator is nothing but number operator, right? So the density of electrons is given by the number of electrons divided by volume. But volume is just a constant. Okay, so in fact, so this operator simply counts how many electrons in your system and what is the time fluctuations of your electron number operator. Okay, so we should be able to represent the Hamiltonian of a Coulomb interacting electron gas not as the Hartree-Fock way, but in terms of rho. Okay, so next time we will start to introduce this second quantized representation of the electron density operator, both in real space and in moment and space. And once we've done that, we could solve the Heisenberg equation motion for electron charge density operator. And then you could get both the, say, the Coulomb screening and also the plasma oscillation physics correctly. So that's the way to go. Okay, so let me summarize. So we know the failure of a Hartree-Fock theory is because the long-range nature of a Coulomb potential. And so to really cut off the long-range Coulomb potential, we need to consider the screening effect. And also, we should consider the density fluctuations like this, and these phenomena should be captured quantum mechanically. So we have the hint already. And next time, we will do it correctly, purely quantum mechanically, to address this density oscillations and so on. Okay, and then we can actually derive such a screening Coulomb potential, in full glory of quantum mechanics, and we can also understand this. And this phenomena has been observed already long time ago, like 40 or 50 years ago. And we could check these predictions from this quantum mechanical treatment of a plasma oscillation to the experimental observations, and they match perfectly. Okay, so we learned a lesson, and so we come from the failure, but we should overcome this failure because we know why and how it fails. Okay, so that's the lesson. Without the failure, we cannot succeed, and if we don't fail, and we may not be able to reach this correct approach. And once we use a good correct language, and the problem is solved. Okay, so the language is not the language, English language. The language is the mathematical language. So once we get the correct mathematical language, the problem is solved. But how do we know this correct language? We don't know unless we fail. So that's the real lesson. Advance in science and physics is based on millions and millions of failures, and we can actually make progress from this failure. So the failures are really, really important, and this is the lesson. And if you look at these textbooks, you will find this progress of solid-state physics from the Heisenberg time to, say, mid-50s, and then nowadays to, say, 21st century. So there are many, many progress in physics, and each progress is really not easy to achieve. So we should appreciate the failure of our ancestor, and we are glad that we live in the 21st century where these mysteries are really solved. Okay, very interesting. So next time we will really get to the hardcore of this, say, plasma oscillations from pure quantum mechanical treatment. But first we should derive this Hamiltonian in terms of rho. And please read these corresponding chapters in Debbie Pine's lecture notes and also Flansburgh. So there are corresponding chapters for this. Okay, so it's fun. We are getting to the fun part of the solid state. And don't forget to do your homework and think about this content. And one more thing, just as I mentioned here, to actually visualize this plasma oscillation, you need to think about this motion of a charge in this cartoon picture. So there are always cartoon pictures that you could use to help you to understand the physics. If you get the correct physics, you must have a picture that you can realize this thing. You should print this message to your brain that physics is about using pictures to understand phenomena. It's always pictures, pictures, and pictures. Diagrams, diagrams, diagrams. The mathematics comes later. So that's the totally new perspective that I can give you to understand physics. Okay, so our time is up. So I'll see you next week.